Let's talk about some more behaviors. Imagine that you are trying to study the population of rabbits in some ecosystem, and if I could denote population with P, and we are trying to see that how does that population change with respect to time, then there is a very famous function that is known as the exponential function, which is written as this, and it depends upon uh, the initial population and an exponential rate as to how it will change with time. So if the initial population were let's say 200, where each notch here represent 100 people, so this is 200, each of these boxes represent 200, then you can see that the rate of increase of the population is this. But if you change the initial population to 1, then you see the rate of increase also decreases, and this can be illustrated if I could add a knob to it, and I could change the initial population to, let's say, each one represents 100, so I could start it with let's say 0.1 and take it to 2, and the step would be 0.01. then you could see that if population starts at 100, then this is the rate of increase, and it is very steep. The population is increasing very fast with time, where x-axis represent time. And if I decrease the initial population, where now it's just it's the 70 people, since 1 represents 100, then 0.7 represents 70 people. As you can see that as I decrease the initial population, and if I zoom in on here, you can see that this is where the graph starts. At time 0, you have, let's say, 0.3 or 30 rabbits in the population. So you can see that the rate has also become shallower. But if I increase the initial population, then you can see that it is growing in rate as well. Well, I just want you to know that any exponential growth or any growth behavior is represented by a function that involves e to the power of the independent variable. Then that is something that you should keep in mind. And in the same way, if something is getting decayed, if something is exponentially going down, then there would just be a negative sign on the exponent, and you will see something like this. Another thing is that if there is a wave-like behavior, so you are trying to compare the vertical vibration on a string to the wave motion that moves rightwards, you will have a function something like this, sine of x, and you will have a wave-like behavior. And keep in mind that I'm going to sort of combine this wave-like behavior and this decaying behavior and try to make an even sophisticated behavior just by combining these two in a while. So you can see that this wave-like behavior could be, this sine x could be used in situations where some bodies are showing wave-like behavior or vibratory behavior, or something is moving in cycles, going up and down between a certain fixed value. So that's sine. You can see that if I write 4 if I multiply 4 with it, the size, the amplitude of the wave grows. So that means I could enter a knob here. So how about I add a knob A here, a slider, and you can see that decreasing it to 0 just flattens it out, and increasing it increases it to the one side, and going down to the 0 takes it to the other side, flips it. So let's keep it at some random value, and you can see that this x, if I add, let's say, 1 to it, then you can see you did not observe it, but the wave moved leftwards. If I add 2 to it, so you can't observe it until I add like a slider to it. So I'll add a slider b, and then you will see that when I move the value to a negative number, it moves to the right, and when I move the value of b to a positive number, it moves to the left. So it's an opposite thing. So that means if I subtract something from x, if I subtract 1, it will move 1 unit to the right. If I add, let's say, 4 to it, it will move 4 units to the left. So something that is adding or subtracting directly with x, or the argument of the function, or the main independent variable, in other words, will cause a left-right motion. Okay, so let's keep it somewhere. What are the other things that we could do to it? Let's see. What if I multiply something before this, let's say 2? Okay, that is causing another type of change. So what if I add another slider here? Can I add another slider here? Let's see, maybe here. Yes, I can add another slider here. So I'm multiplying the I'm scaling up the independent variable input into sine, and you can see that increasing that factor of scaling squishes the wave into smaller region, and so we call this that the wave has a huge frequency. More waves are passing per unit time, so that's how it is. Okay, and it would be better if we talk in terms of time, because I'm about to introduce the concept of time here. So let's see, and so I'm going to bring it to this situation, and I'm going, just for a revision, you know that anything that is directly getting added or subtracted to the independent main variable causes it a left-rightwards motion. Something that is getting multiplied with the main argument is scaling it up. So you can see that having a bigger value, if it's a bigger value, then it gets squished one side, but if you bring it to 0, it closer to 0 it expands, and higher than 0 it squishes like this. Okay, so I hope that you have kept this in mind, and now I want you to sort of remember that we have this other function that causes decay. How about we sort of combine both the behaviors into one behavior, and with that I would like to show a real life behavior, which is that waves die out. So after some time, if you pluck a string, then it moves up and down, but slowly it dies out and the string comes to a rest. So I would like to model that behavior, and you can see that a wave-like behavior that is dying out. So you see that a wave-like behavior that is dying out would come out of the combination of a wave-like behavior and a dying out behavior, an exponential decay and a wave-like behavior. So so I will try to explain that by combining these two functions into one function. So let's say that I multiply. So I am going to write the same function one more time. Y is a function of time equal to k e to the power of minus t, and then multiply the whole thing with a, and then c. How about I just copy this whole thing? I'm just multiplying both the functions here, and I'm going to hide this behavior, and you can see that we have a behavior which might not be very obvious as of yet, but let's just play around with it a bit, and you will see that indeed we are getting somewhere with it. and how about I add one more factor, let's say A is taken, B is taken, C. What about D? A slider D into it, and I decrease the value of D, and you can see that just by combining two types of behavior, one is a wave-like behavior and the other is a dying out behavior, and let's add a D to this as well, then I will sort of at the same time display the result of these two into one graph, and you will see that sort of both these graphs, they have they are following the trace of this decaying graph and also showing the behavior of a wave-like graph. So you can see that just by playing around with these waves, we were able to develop a model of how a wave decay or a dying out wave could be described in mathematical language. And this is a huge accomplishment, and I would like you to play with these graphs, sort of mix and match more graphs like these, and see that what happens to these graphs if you sort of change C, which is a multiple to the argument, and in this case now C is here, so you can forget about these. So this C, if you change it, then what difference does it make on the graph? And if you are changing B, then what is it doing? It's moving the graph rightwards, now it's moving it leftwards. And what does D, which is a multiple in the exponent, cause the change? So you can see that as it moves, so you can see that it has a certain kind of effect on it. And do we have a K? And let's see, the K has an effect of decreasing the magnitude or the loudness of the sound. So you can see that there are several things that you could do just by playing with graph, only if you have added these variable sliders to these. If you put in numbers, then you would have to change those numbers over and over again, and you would not enjoy the experience. So this was a whole conclusion of how mathematical expression could be used to draw graphs which speak or which stand in the place of real life behavior that we see in our observation of nature. So I hope you enjoyed these clips about behavior, starting from the very simple behavior of a straight line, moving on to complex behavior, and I'm sure that over the course of our learning we will see more and more behaviors like these. So hope to see you in the next lesson. Thank you for joining.